please.
Great, thanks, Dieter. Okay, so thank you very much to the organizers for this fantastic conference. Really been enjoying strings very much. And for giving me this wonderful assignment of producing an overview over the field of generalized symmetries. This is a double-edged sword, because when you look at this data, you will see there's lots going on in this field. So this is the paper that came out in 2014, so that's also a 10-year anniversary, just like 40 years of anomaly cancellation, Green-Schwarz anomaly cancellation. Here we have 10 years of generalized symmetry, so to speak. And every year we're producing more and more papers. And so reviewing this field is a huge challenge. I will try to do that in the first part of my talk and give you some idea of what people have been interested in, where the progress has been. And since this is strings, I will focus also on string theory, sort of realizations, applications of this field. In the second and the third part, I will focus a little bit in and zoom in a little bit more and talk about some of the conceptual things that have emerged, which really are extremely fundamental aspects that I'll sort of explain to you. And then there's the last part is applications. So this is really seeing these generalized symmetries at work, not just we have constructed them, but actually what can they do for us. Okay, so overview of what has been going on. In 2014, the paper, really the most sort of striking insight that's sort of been the game changer in all this is that they identified topological defects in a quantum field theory as global symmetries. And so you relax all other conditions, just topological defects. This led them to think about higher form symmetries, so things that act on extended operators, or higher group symmetries, so these are multiple higher form symmetries that mix together. But in the last few years, and this will be the main focus of my sort of overview, the extension has been to so-called non-invertible, or in the case you're not scared of the word, categorical symmetries. And I will use these two things completely interchangeably. What you should really keep in mind, what is that non-invertibility? When you have a group, you have an inverse. Here, basically, you compose two generators, A and B, and the result is generically a sum with non-negative integer coefficients of other generators. So this is more like they have a sum and a product and a sum, so it's more like an algebra, but actually mathematically it's a bit more structure there, and it's a fusion category. It's just a terminology that mathematicians have invented here. There's a long history of this in two-dimensional quantum field theories and rational conformal field theories in particular, but the excitement has been about these higher dimensional realizations of such symmetries. So this has led, as I just showed you in this plot, to this huge number of papers, particularly in the last couple of years. What I think is really exciting in all of this is also this cross sort of fertilization between high energy theory, pH, as well as condensed matter and mathematics. And you'll see that this really seeps into the field very strongly. Okay, before we actually go in and see what people have done in the last few years, we go back to the very, very beginning and look at something. There's no question about what the system is, what it's about. It's a very simple model. It's a transverse field easing model. It's a spin chain with L qubits, up-down spins with nearest neighbor Hamiltonian. So you have sigma z's and sigma x, and there's some coupling G. This Hamiltonian has a Z2 symmetry. It's just a spin flip. Up goes to down and vice versa. If you now look at the phase space of the spin system, there actually a G goes to small, so when this is negligible, there are two ground states, all up, all down. The Z2 exchanges them. So that's kind of like a Z2 spontaneously broken symmetry phase. When G is large, then in fact the second term dominates, and then the Z2 is preserved, and this is the disordered phase of a single ground state. And of course, at G equals to 1, we have the critical easing CFT, which is this equals to 1/2 CFT that sits at G equals to 1. Now this spin system has a duality. This is this Kramers-Wanier duality, which maps X to ZZ and ZZ to X, or just G goes to 1 over G. So this maps basically one spin system to another, except that G equals to 1, it's a self-duality symmetry, and this is sort of the epitome of a non-invertible symmetry. It's like, it's a self-duality, it maps the system back to itself, and in fact it satisfies this particular relation. N squared is 1 plus eta, where eta is the spin flip. So if you now abstract this is basically an Ising fusion category symmetry. It's realized in the spin model. It has a Z2 group, but then it also has this non-invertible defect n, and n squares to 1 plus eta. Another very simple class of non-invertible symmetries come from non-abelian finite groups. I should say something here. Most of the things I'll talk about finite symmetries. I will hardly talk about continuous symmetries, so please keep that in mind. So finite non-abelian groups, their representations form also fusion categories. For example, take the permutation group on 3 elements, S3. It has a trivial representation, a sign representation, and then there's a 2-dimensional representation. And this 2-dimensional representation here has a tensor product that decomposes into this way here, into the irreps. And this you can now interpret in terms of a fusion category, which is called rep S3, and it's a non-invertible fusion because you had a higher than 1-dimensional irreducible representation, and that's a feature of all finite groups. Okay, so that's all in 2 dimensions, and now what happened in 4 dimensions? Well, so there's sort of the analog of the Kramers-Vanier duality exists also in 4 dimensions. It sort of started off this whole field. There's a 4D version of that. You have a QFT, you have a duality, you go to a particular point in the parameter space of this theory, and the theory is actually self-dual that constructs for you. Well, is there a problem with the audio? Okay, because you're like, be more quiet. Okay, so it's a self-duality, and that creates for you a defect, a codimension 1 defect, so it's a non-invertible zero-form symmetry. The idea is completely analogous to the spin system I just talked to you about. There's also a class which is called condensation defects, and those are constructed by taking a higher form symmetry and gauging it not in the full space-time, but on a subspace. And that's sort of condensing that higher form symmetry, and these give also non-invertible defects. And then you can also look at gauging of auto-automorphisms. Maybe that's the most intuitive thing. If you have an auto-automorphism, for example, the simplest example is spin 4n gauge theory. It has a Z2 times Z2 in 4 dimensions, Z2 times Z2 one-form symmetry. The auto-automorphism acts as exchange. When you gauge that, you need to take this linear combination of these 2 generators, and that, of course, if you now naively calculate the fusion of that with itself, will have a couple of terms. So it's non-invertible, sort of, by just looking at this operator here. So these are sort of 3 canonical ways of getting non-invertible symmetries in higher dimensions. The mathematical structure is now not a fusion, but a higher fusion category. It has defects from dimension d-1, which are zero-form symmetries, all the way to 0-dimensional defects. And at each level, you have a fusion. And then you have consistency conditions and some completely complicated mathematical structure, and mathematicians call this the d-1 category, higher fusion category. So this may not be the object that you would like in your life. It sounds very complicated, but what I'd like to convince you is that really in every aspect of your life, you're a string theorist working on the worldsheet, you're a geometric engineering person, you're a swarm plant person, you're a holography person, you're a brain person, you might want to do the standard model here at CERN, or you're a lattice person, or you're just interested in formal aspects of quantum field theory. All of these things will have non-invertible symmetries. And of course, I can't cover all of these applications, but since last spring, luckily, we have lots of reviews. They all came out at the same time, basically, so you can also look at those for more inspiration. So let's see how the string worldsheet, I will just go through all of these points now and explain to you sort of roughly where these non-invertible symmetries come from. So in two-dimensional conformal field theories, rational conformal field theories, it's well known since the work of Alinde, Petkova, Zuber, and others that there are topological lines that have fusions that are non-invertible. In fact, they're labeled by the primaries. If you have versor minimal models, they're labeled by the conformal weights, and they have a fusion given by the fusion coefficients of this minimal model. So for example, the Ising model, C equals to 1/2, is a minimal model that has exactly this non-invertible fusion, and this eta and n line are these two L1/2 and L1/16 lines. This has, of course, had lots of applications in 2D rational conformal field theories. I want to actually highlight one particular application that came out very recently. It's a really nice application studying sort of the implication, physical implications on RG flows of these things. If you have integrable flows away from some CFTs, they commute with the Verlinde lines or a subset, then you can constrain the scattering, and in fact you get modified crossing for the S matrix. This is work by Coppetti, Lucia Cordova, and Shota Komatsu. Okay, but how does the string worldsheet come into this? There are these beautiful constructions by Gepner, who said particular points on the Calabi-Yau sigma model actually have a description in terms of a tensor product of minimal models, n equals 2 minimal models. So they're rational conformal field theories with respect to that chiral algebra. So you take a tensor product of minimal models modulo some finite quotient. The minimal models have a coset realization, and of course, the minimal models have these Verlinde lines, and the coset and this quotient will also inherit some of these lines. So there's a non-invertible symmetry in these Gepner models and the Calabi-Yau sigma model moduli space. And that sort of, that has been sort of discussed in these two papers very recently. Question is, what is this good for? One really nice application is Gepner points are simple. Going away from the Gepner point is extremely difficult, and what you can do is some of these exactly modular deformations will commute with these non-invertible lines, and so you can track some things that can constrain the spectra and correlation functions. So for example, if you take the quintic threefold, this Calabi-Yau threefold, this is this minimal model here, and there's a subspace of exactly marginal deformations that commute with a Fibonacci fusion category, so a subcategory, which is the simplest category you can think of. W squared is 1 plus W, and that constrains sort of what happens away from this Gepner point. So that's a very nice sort of string theoretic application. Let me go next to the string theory and geometric engineering side. There's been a beautiful review on this by Iñaki in Strings 2022. So I don't want to go into too much detail. This is about asking, you have a string compactification, M-theory, string theory, on a non-compact special holonomy space, and you would like to understand, you engineer a quantum field theory in this way because you decoupled gravity, it's a non-compact space. How are these generalized symmetries of the quantum field theory encoded in that space? So the first insight is that, in fact, the topology of the space relative to its boundary also actually will capture all of these generalized symmetries. So in this case here, there's the relative homology, so x del x, over the actual homology degree p plus 1, say. So the way you should think about this is these are these infinitely heavy particles or probes modulo screening. So for example, in M-theory, having a non-compact 2-cycle wrapped by an M2 brane gives an infinitely heavy particle, so that's a line operator. And then you have also M2 branes wrapping compact 2 cycles, and they will screen these line operators, and that's this quotient by the compact cycles here. So this is just basically saying the line defects are the infinitely heavy, the non-compact cycles modulo the compact cycles. So this encodes, basically topology encodes all these symmetries. Also, the topology encodes the Toft anomalies of these generalized symmetries. That's obtained by reducing the topological couplings in M-theory or type 2b on the boundary of the space, and it gives you the anomalies. It's like an anomaly theory, but actually nowadays it goes under the name of the symmetry TFT. Of course, there's a question how you make this all compact, and I think Miguel talked about all the swampland implications of this topic. Okay, there's sort of the third application is strings in holography, and there's one particular case that's sort of more closely related to the case of the 2D CFTs that I talked about, and it came out literally in the last week or two. One paper came out yesterday. If you look at holography, you can ask what are sort of the realizations of the generalized symmetries, in particular non-invertible symmetries on the boundary, from the boundary in the bulk. So in ADS3 CFT2, the situation is a bit special. The non-invertible symmetries that come from the SN orbifold, so the symmetric orbifold CFT, that's the two-dimensional CFT. And in fact, they have naturally these non-invertible defects. So like this is related to this rep SN that I was talking about at the beginning. So one question is, how do you identify these non-invertible defects in the bulk ADS3? And these people here have sort of written some indications that there could be some identification with bulk worldsheet string operators in the tensionless limit. The situation in the other holographic settings is slightly different. There, basically, it's useful to just look at the supergravity approximation, ADS5, ADS4, Klebanov-Strassler, and also duality defects. And I want to dig in a little bit more into this. This is very familiar to most people, but it's also sort of tying into this concept of the symmetry topological field theory, which has been this guiding principle throughout these symmetry developments. So how do I see in ADS5 times S5 what global form of the gauge group I've looked at, right? So we always write SUN, but really you haven't really written down SUN. You've written down, first of all, just a relative theory. You've given a gauge algebra math frag SUN. And the question is, how do you actually specify the global form of that in this holographic setting? So Witten already noticed all this. This is from 98. Really, this is nothing new. This will be invertible. This is about the one-form symmetry of n equals 4 superangles. And you notice that basically the leading sort of a derivative expansion of the action in ADS5 has a coupling which is n times B2 DC2. B and C are the two forms NS and S and RR. So this is a BF coupling. It's a topological coupling for ZN two-form field B2 and C2. So we should think of these as the background fields for the one-form symmetries. They are now topological defects in 5 dimensions, the holonomies of these B2 and C2. And because we're in 5 dimensions, surfaces will non-trivially link. So in fact, those two things are not really commuting. They're actually not neutrally local. B2 with C2, you exchange them. They pick up a phase depending on the linking of the two surfaces, and then you've exchanged them. So this linking basically says you have to now actually pick, when you go to the boundary, you have to pick some subset that you now declare to be the actual one-form symmetry of the boundary theory. In fact, you want to pick a maximal subset of these things. So you want to pick basically, for example, the B2s to be Dirichlet and the C2s to be Neumann, and then the B2s actually will end, the surfaces will end, they give line operators, and the C2 will give rise to the Neumann boundary conditions that give rise to the symmetry generators. The linking in that case, once you go to the boundary, will be precisely the one-form symmetry generators will actually charge the line operators. That's the picture. So this is how you now specify, once you specify this here, you specified a particular gauge group for your holographic setup. So this is invertible. How do I get a non-invertible symmetry? So this is actually happening in the context of the Klebanov-Strassler solution for the n equals 1 SUN super Young Mills. So we know this flows to a confining theory for SUN. So if you look at the topological couplings in that context, so you look at the same sort of truncation, you still have this NB2DC2, so this is the BF coupling. That's just saying you have an SUN gauge algebra. But then there are additional couplings. There's a zero-form symmetry in its dual. It's a Z2N, that's the chiral symmetry. And then there's a coupling, which is a mixed anomaly between the zero-form and the one-form symmetry. So this is the modified leading order expansion of the supergravity action in 5 dimensions for this Klebanov-Strassler solution. In this case, you have a zero-form symmetry, and you would write down normally the generator by just the holonomy of C3. But here, if you take the PSUN global form, so not the SUN, but the PSUN, in fact, putting those boundary conditions in, the generator for the zero-form symmetry here is not C3, but you have to address it by these additional couplings, and it's due to these anomalies, this mixed anomaly between the zero and one-form symmetry. And this is now actually a defect. When you compute the fusion with itself, it's non-invertible. So in fact, when you fuse it with n dagger, you get the condensation defect for the one-form symmetry. So this kind of operators you get automatically in these holographic settings whenever you have such couplings here, and you need to define sort of consistently, a gauge-invariant way, the symmetry generator. Okay, so this is essentially how you realize non-invertible symmetries in holographic settings. There's been sort of another slightly complementary development, which is saying all of these constructions rely on this bulk supergravity or string theory. In fact, all of these topological defects that generate the symmetry have an interpretation in terms of placing branes into some supergravity background in a particular limit. So the conjecture or the proposal, which has been checked by many, many people in different contexts, is if you place branes in the near horizon, they become sort of topological objects. All the dBi actions become trivial. The only thing that remains are the Westermino couplings, and then you get exactly these topological defects that generate the symmetries. So in this context of the n equals to 1 holographic duality, for example, the brane that generates this non-invertible symmetry is a D5 brane that's wrapping, that's wrapping in S3 inside the compactification space T11. And if you look at the topological limit of this brane action, it gives you precisely this thing that I was telling you is dressing this zero-form symmetry generator. So this seems maybe a coincidental thing, but actually it sort of works in many, many contexts. And also there are other ways to sort of substantiate this. You could ask, well, this is a non-invertible defect. How do you see the fusion from the branes? In fact, the fusion from the branes is you take this n with n dagger. This is a D5 anti-D5. They will just annihilate, but in fact, there's flux on there. There's a D3 charge on there. So in fact, at the end, you get a condensation defect from this as the end product of the tachyon condensation of the D5 bar. So the brane fusion, the fusion is basically tachyon condensation on the branes. And then you can ask, how do the symmetries actually act on charged objects like Toft lines in this PSUN theory? So the Toft lines are essentially given in terms of D3 branes, and the linking is given in terms of D5s and D3s linking in the space-time of this Clapeyron-Strasser solution. So for example, if you wrap the D3 branes, it has to be a heavy object, right? So it's wrapping the radial direction times an S2 times S1, and then the D5 brane is the symmetry generator. And you can ask, how do I see the action on the Toft line? And this actually is simply, if I move a D3 brane through this D5 brane, there's a brane creation, it's like your string creation in this case. There's the Hanani-Witten move that creates this sort of attachment, flux attachment of the Toft loop as it moves through the duality defect. So string theory seems to know about all of these effects quite naturally. It's sort of the action of non-invertible symmetries on line operators is basically Hanani-Witten in this context. One nice feature here that we can sort of point out immediately is, right, so here this is the action of there's a genuine line operator. I move it through the topological defect, or I move the topological defect through it, it becomes this flux-attached line operator, right? So this is this Witten effect. There's a general feature that you map with non-invertible symmetries genuine operators to non-genuine operators, where non-genuine operators are things attached to topological defects. So this is sort of different from standard group-like symmetries. You've not seen this in group-like symmetries, and will be one of the questions how we actually study representations of such non-invertible symmetries. Okay, so string theory basically has, for all of these symmetry things, there is a counterpart in string theory or in holography that explains for you these mechanisms. Okay, there's the next application is to start the standard model. There were 2 talks in 22 and 23 already on these type of applications. We heard some of that yesterday. The construction in a slightly different context. I don't want to go into too much detail here. The key construction is, again, there's this ABJ anomaly. It means you need to dress this zero-form symmetry generator by this TQFT, which is essentially U1 level entry on Simon's theory, and it becomes non-invertible. And this now can be applied in many, many contexts, reformulating pion decay constraints, the non-invertible U1 Peccei-Quinn symmetries, etc. I think none of these things are yet sort of smoking gun applications to the standard model, but there are certainly really nice indications that this can be relevant for actual real-world physics. Okay, so other real-world physics applications are lattice models, and I'll sort of maybe make the point that condensed matter theorists are much more open to the concept of categories and realizing categories in their lattice models. So there's this beautiful construction in 1+1 dimension called the anion chain. You give me a fusion category, it spits out a chain, a spin chain, that has this fusion category symmetry. And there are many sort of subtleties regarding to this anion chain related to whether the Hilbert space is a tensor product Hilbert space or not. Lots of work on this particular question also has been by Nadi and by Shuhang and others. But one exciting sort of development has been that there are new types of phases one can construct in these lattice models. You write down a UV lattice model and it realizes, for example, non-invertible symmetry-protected phase. And this is exciting for these condensed matter people, and I think it's an extremely nice application of all these works. There's also the sort of extension to higher dimensions. So Inamura and Omori wrote down a 2+1 dimensional analog of the anion chain. They have a 2 fusion category that's valid for 3-dimensional theories, and there you can now play the same game. Okay, so this is the end of this summary. And I think one thing that you probably should take away from this is there's an abundance of non-invertible symmetries, and they come up in many, many different contexts. So maybe you can't quite ignore them. But there's also sort of a question, what do they really do for you? Like, how do they sort of give you some interesting physics? And this will come from essentially these applications in low-dimensional systems. So I would like to address in the remaining time 2 questions. The first question is sort of a fundamental question that once you have a new type of symmetry, you want to ask this question immediately. You have a group symmetry, you know everything in your theory, the operators, everything will just be transforming in some representation of the group. So in quantum mechanics, we know this from the works of since the 1920s. So you can detect the representation by taking an operator, it could be an extended operator, wrapping a topological defect around it and computing what the charge is, how it transforms. So you know groups implies representations. What is the replacement of that for non-invertible symmetries? And I like to call these things, these new kinds of representations, generalized charges, because they're kind of from generalized symmetries to charges. And the second question is, when you have symmetries, one obvious question is, can you use them to sort of classify the phases of quantum systems in the IR? You have a UV symmetry, what happens in the IR? And this is generalizing this Landau paradigm, which says if a continuous phase transition will be a symmetry-breaking phase transition. So for groups, this is well known. You can break from a group to a subgroup. Then you get G mod H, if the subgroup is H, G mod H many vacua, and the remnant group, this remnant symmetry will act on these vacua. So the question is, how does this now generalize to non-invertible symmetries? The Z2 case, I've put it back here, but it's basically this Ising chain that we talked about at the very beginning. Z2, spontaneous symmetry breaking, SSB phase, a trivial phase, and in the middle you have then also transition, which is a critical model, so that's what we would call a gapless model, this is the Ising CFT. Right, this second order phase transition is basically between the Z2 SSB phase, this spontaneous symmetry breaking phase, and the trivial phase. Those are topological phases, and at the critical point you have the Ising CFT. So that's a Z2 transition. If you now have a non-invertible symmetry, what happens? How does this story change? And that's sort of this categorical Landau paradigm, which I'd like to tell you about. So question number 1, what are these generalized charges? The generalized Q charge is a Q-dimensional defect transforming in some representation of the non-invertible symmetry. So to formalize this, it's useful to look at, again, two-dimensional examples. We've seen sort of how the non-invertible symmetry acts on the Toft lines in this PSUN theory. A very similar action you can see also in the Ising model. Remember, this was the fusion category symmetry, n squared is 1 plus eta. If I act with that on the spin operator sigma, then in fact I can move this through. It's topological. I can sort of bump it out like this here, and then I can use the fusion, and then I get here, n with n actually gives a non-trivial eta line. So the non-invertibility says, again, you from sigma, which is a genuine operator, you go to mu, which is a non-genuine operator that's attached to the Z2 line. So again, non-invertible symmetries map these genuine to non-genuine operators. So you should really think of those two operators being in the same multiplet representation of this non-invertible symmetry. So this can be studied, and this is this reference here, in terms of mathematical structures called tube algebras and the lasso action. It's a little bit more elegant to actually just think about this SymTFT picture, which is saying all of these actions of the non-invertible symmetry have a nice linking interpretation of topological defects in the SymTFT, which is a d plus one-dimensional topological field theory. And it's constructed based just on the symmetry. For the invertible Zn symmetry, it's just the BF theory. But we'll see in more complicated non-invertible settings, it's a little bit more complicated, and you get these slightly more intricate actions. And by looking at the SymTFT, this action on the symmetry on the defects will become much more transparent. So this is sort of the moment when I need to tell you what actually the SymTFT is. And I'm sure you've heard a lot about the SymTFT in different contexts, but it's essentially, you're given a theory of a quantum field theory with a symmetry, invertible, non-invertible, finite for the moment, in d dimensions, then you can gauge that symmetry, but not in d dimensions, but in d plus one dimensions. So you essentially couple it to an S symmetry gauge theory, and this is the SymTFT. So for the BF theory, that's just a Dijkgraaf-Witten theory for Zn. But more generally, this is a well-defined mathematical construction how to get from the symmetry the SymTFT in this way. And it's compactified on this interval in d plus 1d. And it's a sandwich construction between one bread is the symmetry boundary. That's where all the symmetry aspects are. So all of your topological defects that become the symmetry have Neumann boundary conditions there. And then there's another boundary, the other side of the sandwich is the physical boundary condition, and that actually is not necessarily topological. That's where all the dynamics is happening. And the paradigm is if you compactify, this is the TQFT, you can compactify it back to d dimensions. This is basically the theory with the symmetry action. Okay, and the main players of the SymTFT are the topological defects of this theory. Just like these holonomies of B2 and C2 in this Dijkgraaf-Witten theory and the BF theory, here also the topological defects will be key. So first of all, how do we recover the symmetry? As I said, it's the topological defects that basically have Neumann boundary conditions. So you on the symmetry boundary, you just take the topological defects of the SymTFT and you take Neumann boundary conditions, you project them, and they will generate the symmetry. You can mathematically define this in terms of something called the Lagrangian algebra, which is basically saying it's sort of the complement of the guys that are the symmetry, so the ones that are essentially not mutually local with them. So these are the ones that will end on the symmetry boundary. So that's a Lagrangian algebra. And these are sort of maximal boundary conditions or gap boundary conditions for the SymTFT. How do I get the charges, so the charged operators? Those are coming from topological defects that end on both boundaries. Why is it important that it ends on both boundaries? Well, there's a linking in the SymTFT, just like in this BF theory. And the linking is the charge. Right? So basically, if I have two topological defects that have the non-trivial link in this d plus one dimensional theory, I can push these blue guys to the boundary, they become the symmetry. Then this Q, this line that stretches between both boundaries, becomes the actual charge, And then the linking is just how the symmetry actually acts on this charged operator. So the generalized charges are just the topological defects in the SymTFT with these boundary conditions that they end on both sides of this interval. And the linking is the action of the symmetry on the boundary. You can also in this way construct the non-genuine operators by these type of configurations. And using this structure, we can now determine how non-invertible symmetries or invertible symmetries act on defects. So let's look at this for groups. So for just non-abelian finite groups. And this seems like a trivial example because we're just looking at non-group-like symmetries, but in fact, the SymTFT is invariant under gauging. So the SymTFT for the group symmetry is the same as the SymTFT for the dual symmetry, so the RAP-G symmetry. So for non-abelian group, the topological defects in 1 plus 1D are just labeled by conjugacy classes and the representations of stabilizers of the conjugacy class. For the S3 example that we looked at the beginning, this is just completely explicitly determined in the slide here. So conjugacy classes are listed here, and the representations of these conjugacy classes are here. And now this is sort of determining the bulk topological defects. So these are essentially just the whole list of topological lines in this topological order that's this SymTFT for S3. Now we're asking, what are the symmetry boundaries? We'd like to recover the S3 symmetry, but also the RAP S3 symmetry. And these can be classified in terms of some mathematical structure called these Lagrangian algebras. And in fact, there are 4 boundary conditions. And 2 of them are the ones that we know, S3 and RAP S3. And now from this, if we pick one of them, we can determine the charges under these various symmetries, right? There are now these topological defects that stretch between the 2 boundaries, and the linking action in the bulk will give us precisely how these multiplets work. In the invertible S3 group case, this is not very interesting, but in the RAP S3 case, you see again, there's a multiplet of an operator, genuine operator, and a non-genuine operator. The non-genuine one is attached to this topological line, and they're in one multiplet, and that's something you determine from the SymTFT action. This is the explicit way that the action of the symmetry is on these operators. And you can see the genuine operator maps to non-genuine and genuine and so on. Okay, so SymTFT basically has the key features of the topological defects in it. It's sort of gauge invariant because if I gauge a symmetry, the SymTFT doesn't change. All that changes is the boundary condition of the SymTFT. It captures Toft anomalies, but the beautiful thing is this construction of the SymTFT or its topological defect are mathematically extremely well understood. This so-called Drinfeld center is just a set of topological defects for example, 2 fusion categories. So this is something that you can tap into in the mathematics literature and then extract out all the possible sort of bulk topological defects and then study the physics of it. Recently, people have tried to extend this to continuous symmetries, and I've listed several papers on this. I think here there's still some clarifications in future works to be done, what the right framework is. Okay, so we've learned how symmetry, non-invertible symmetries, can be sort of how the representation theory of them works, and it works basically best in the SymTFT picture. Now I want to actually tell you how we use this to do some interesting sort of application. And that's work in collaboration with these wonderful people, Laksha Bhardraj, Leah Bottini, Daniel Payer, Alison Warman, and our condensed matter friend Apurv Tiwari. So here you already see that this is really already a HepTH CondMat collaboration, and there are many, many works that we've done with these condensed matter theorists, both in the continuum and in the lattice. So and there are lots of related works by condensed matter people and by HepTH folks on gapped phases, gapless phases, with fermions, on the lattice and in the continuum, and this is sort of a set of references for you. The question is, given a symmetry that's non-invertible, how do I extend this Landau paradigm of symmetry breaking? So the question really concretely is, I give you a symmetry, and now tell me what are all the gap phases and what are all the phase transitions between them. And when I study the gap phases, what actually are the order parameters that give, that pick up a non-trivial vacuum expectation value. And for this, I need to know basically the whole representation structure of the non-invertible symmetries. And so this sort of built up a categorical Landau paradigm, and in this way you can explain certain phase transitions that are not explainable by just group symmetries. That's the whole point of this enterprise. How do you construct gapped symmetric phases, so topological phases with a symmetry? In the SymTFT, this is just slotting in, instead of a generic physical boundary, another topological boundary condition. So, the SymTFT had the symmetry boundary that determines the symmetry structure, and now you had a physical boundary, and there you could put in, I don't know your favorite quantum field theory, but now I'm saying I want to have topological field theories in d dimensions with a symmetry S, so then I slot in just a topological boundary condition there as well. So these are the sandwiches that give TQFTs. Mathematica, again, this is sort of slotting in these so-called Lagrangian algebras. In terms of the rough classification of phases, there are sort of these spontaneous symmetry breaking phases. Those are really much like, the symmetry, non-invertible symmetry is broken to a subsymmetry. But then there are also interesting new sort of symmetry protected phases. So these SPT phases are essentially such that they have a single vacuum. So you have just a single vacuum, so it looks like a trivial theory, but actually you can't deform the theory to the trivial theory without breaking the symmetry and closing the gap. So this is sort of a very nice class of symmetry protected phases, and these SPT phases you can now also construct with this mechanism for non-invertible symmetries. The number of vacua can be read off from the SymTFT, but just the number of topological defects that can end on both boundaries. And so you detect actually also in terms of the number of lines and how these different Lagrangians actually intersect the structure, whether it's SPT or an SSB phase. Let's do this for groups, because this we know extremely well, just to sort of very briefly, yeah, thank you. Just to briefly sort of set the scene, you have a group symmetry, it can break to a subgroup H, SSB phase, or it can have an SPT phase. For Z4, this is simply that SymTFT is a Z4 Dijkgraaf-Witten theory. There's just this BF theory. The topological defects are these lines, E and M. You have now a 3D TQFT, so it's some topological order. Its lines, its anyons are now E to the I, M to the J. And now we can look at what are the gap boundary conditions. So this is just what are the maximally mutually local lines that can sort of end at the same time. There's an electric boundary condition that gives you a Z4 symmetry, zero form. There's a Neumann boundary condition, which is the magnetic one, which says there's the dual Z4, but you could also have sort of, you just gauge a Z2 inside the electric Z4, and that's the third one. So if you pick the electric one as the symmetry one, then we can write down now all the different possible phases. There are three, because there are three of these algebras, and you all know the answer to this, but I'm now showing to you how to do it in the SymTFT. So if you have both symmetry and physical boundaries to be these electric boundary conditions, so this is the ones that can end are the E lines, the electric lines, then you get 4 vacua. This is the Z4 SSB phase, the spontaneous broken phase. Good. If you have the electric and the magnetic, there's only one line that can end, so you get a Z trivial phase and the Z4 X trivially. And then there's the Z2 one, where you basically only half the lines can end. There are 2 now, there are 2 vacua. That's the Z2 SSB phase. So this is basically a way of getting what you know, but now this you don't know when you have the Ising fusion category. What are the gap phases with Ising fusion category symmetry? So again, we do the same game. We write down the SymTFT, the boundary condition. There's just one topological boundary condition, and so we get a 3 vacuum gap phase, and we can also determine how the Ising fusion symmetry acts on these 3 vacua. right? And this non-invertible symmetry basically maps these vacua into sums of vacua. So this is the sort of action of the symmetry, the non-invertible symmetry on these three vacua. Now this is something you can't do with the standard sort of group theoretic lambda. And then for rep S3, similarly, there are now 4 of these, and you can now go through, write down the vacua and the action of the non-invertible symmetry. So these are all the phases, topological phases, that are rep S3 symmetric. The spontaneous symmetry breaking phases, a trivial phase, and then there's sort of the sort of partially symmetry broken phases. Okay, so the next question is, when you have these topological phases, how do you transition between them? Like in the Ising case, where you have a Z2 SSB and a trivial phase, you go through the Ising critical model. So how do I actually construct gapless asymmetric phases in this way? And, well, we have the 2 sides, the left and the right, and they give rise to these gap phases. Those are these constructions I just told you. The gapless phases you get by now looking at ending not just a maximal set of topological defects, but actually sort of a non-maximal. It's just a condensable algebra. It's not a Lagrangian, not a maximal algebra. When you do that, in fact, you get an interface to a reduced topological order, and that determines basically this transition between these 2 phases. So this, for example, and I can now classify all the different algebras that can exist for given symmetry, TFT. For Z4, this is sort of the set of algebras which all sort of have this partial order, so you can look at sort of a Hasse diagram for these algebras. These are the Lagrangians, these are the gap phases, these are the gapless phases, and then there's the single one where you just have a generic Z4 symmetric CFT. And now all of these will have some particular features. Are they spontaneous symmetry breaking phases? Are they gapless or gapped? If there's a G in front, there's a gapless SPT. So this is something that basically is like an SPT phase, but it is gapless. An IGSPT is an intrinsically gapless SPT. So this is a GSPT you cannot deform to a gapped SPT phase. The same for SSB phases. There are gapless versions of SSB phases and intrinsic versions of that. So now all of these phases will have different type of deformation properties. And one sort of crucial thing is this one here. So if you, for example, pick the electric Z4 symmetry, then in fact this phase here is a gapless phase. It's an SPT phase, but it cannot be deformed to an SPT itself. So this is the SPT phase. So this is what you would call an IGSPT. So in this way, you can now construct the full set of phases, gapped and gapless, and their transitions for symmetries. Here this was Z4. You can now do this for more complicated theories like rep S3 and get these kind of diagrams with all these symmetries realized on the gapped and gapless transitions. One interesting thing is to ask then how do they fit together, and can you actually construct models that realize these phases? And that's where the beauty of these lattice models come in. You can actually write down a spin model that has a rep S3 symmetry, for example, and then map out the full phase space of that and see these 4 gap phases that I talked to you about, and see also that these transitions are Ising, Potts model, and some 2-universe Ising type transition. So this is some work that also was done at the same time by Xiaogang Wen and his people. So really constructing the lattice models that realize all of these symmetric phase transitions for non-invertible symmetries. Okay, so if you sort of tune down, this is the moment to sort of come back. The roadmap, if you would like to construct symmetric phases for categorical symmetry S, and this can be extended to higher dimensions. You take the SymTFT, you look at its topological defects, you write down all the topological boundary conditions, so all the gap boundary conditions of the SymTFT. You pick your symmetry, and you slot in all the topological boundary conditions, and you calculate how many vacua there are, that's how many different lines can stretch between these. Those are the order parameters. Those determine for you the gapped phases. If you only look at algebras that are not maximal, you also get the transitions between two gapped phases. And then you can repeat that. You can have sort of multi-critical points higher up this chain. So I just showed you examples which had 3 layers, but this can have many, many layers, for example, REPT8. And the SymTFT will tell you both number of vacua, the action of the symmetry, and the various order parameters that will be relevant in each of these phases. Okay, so am I on time, Dieter?
Yeah, you are still on time.
Okay, good, perfect. So in conclusion, I also didn't send in actually questions for Hiroshi and Andy, so this is also my homework for that list here. I think one thing that's clear is that these non-invertible categorical symmetries are essentially everywhere, and I think it's very difficult to sort of escape them, so I think you should stop worrying and learn about categories. And it's also extremely tangible. These are not just some abstract constructions. They really come in lattice models. Like, you can't get more concrete. They are in quantum field theories, in 3D, 4D. There are many interesting questions related to extending phases, and this whole story of SPT phases, gapless SPT phases, is extremely interesting, also in high dimensions. I think we'll hear about this from Thomas in his talk in 4 dimensions. Can one actually classify them? And there the whole sort of higher fusion category structure will come in, because you're not just dealing with 1+1 fusion categories as we've been doing so far. One question is there a Landau-Ginzburg type model for these type of transitions that we discussed? The symmetry TFT does not include yet space-time symmetries. And there can be anomalies between space-time symmetries and internal symmetries. That happens in lattice models, for example. So one question is, can one extend that SymTFT to this? And from a more string theoretic perspective is, how does the whole structure of higher fusion categories really emerge from a string theoretic framework? Like, we've seen how the brains realize the symmetries, and the fusion is tachyon condensation, the linking is Hanani-Witten, but can one sort of get the full-fledged structure, the condensation completion, etc. And indeed, developing more tools to constrain quantum field theories, RG flows, would be very exciting, not beyond the 2-dimensional things. And then, of course, connecting it to lattice constructions that will give you some more computational handle in all of these things. Okay, now if this has excited you and you want to sort of have more of symmetry talks, there's lots going on. This is just 2 things. We have a conference in Oxford, August 12 to 16, called Symmetries 2024. And it's essentially a conference where high-energy theorists and condensed matter and some mathematicians will come together and try to talk to each other. And then there's a long program next year at a KITP. There's also a CondMat high-energy collaboration with Mason Barkeshley, Michele Del Sotto, Shu Hang, and myself organizing it. So you can still register for that. So thanks very much for your attention.
Thank you very much, Sakura, for this wonderful talk. We have now time for questions. So please use your microphone in case you want to ask a question.
For the symmetry TFT, you seem to focus on the for the bulk symmetry TFT and also for the boundary. You seem to focus on the non-spin case. Could you comment on the spin cases?
Yeah, you can also extend this. I mean, there were some papers by Laksha, Purv, and Inamura, and also Huang on spin models. So people models essentially extending the whole program to things with spin. So that exists as well. So you just have to add in all the supervector spaces and all this.
Hi. I want to make a comment maybe related with my talk yesterday. I will restrict attention to zero-form symmetries in dimension greater than 3, for example, 4 dimensions. What I would like to say is that to say that there are non-invertible zero-form symmetry in higher dimensions is not incorrect, but it's quite misleading because it can suggest the idea that you can test that in an accelerator, for example, to find something like this in an accelerator. And this is not the case. What people is doing is rather to see how the symmetry, that is a group in that case, can be broken down because you put boundary conditions or you put the theory in a manifold. But for the local physics, it's always a group. And this is important. I would suggest really to look back at the DHR theorem, because it's a theorem done by mathematicians a long time ago, where people do not care about that, because you say, well, this is going to be always, this thing, this topological operator is always going to be a group, right? And people say, well, in that epoch, always the symmetries were groups. But if you want to see this again now with a different perspective, you have to go back to this theorem because it tells you exactly that. That's
so I want to, yeah, thank you for the comment. Basically, that was the same comment I made in your talk at the end, that I'm not making any claims about continuous symmetries. This is all about finite symmetries. And so there's this lattice model by Inamura and Omori that basically realizes two fusion categories. Put it somewhere here. Anyway, there you can, right? The reason why I brought up these lattice models is because there's no ambiguity there. I can write down the operator, quantum mechanical system. So now I actually will construct a 2+1D lattice model with a non-invertible, I don't know, 2-RAB-Z2 symmetry.
Yeah.
Would you call this is just a formalism, and I've actually written down the non-invertible defect. I think this is a big questionable, no?
No, I'm talking about continuous quantum field theory.
That's right, so that's why I think there's a...
Continuous quantum field theory, and the second point is that maybe what you are saying that is a non-invertible symmetry can be just a group if you take a non-abelian group and you make the orbifold, it will give you something non-invertible, but it comes from a group. You know, the conjugation classes of a group form something that is non-invertible, but this comes from a group. And
it's true.
Perhaps you are talking about something different, yeah. Something different means that it not comes from a group, in that case, in that lattice model, right?
It's, okay, in that case, maybe we should do this offline, but certainly there are non-invertible symmetries in 2+1 dimensions, and they can be realized on lattice models. So then the question is, in what sense are they actually invertible? Because your point is what I was talking about is a two-dimensional, it's just limited to 2 dimensions. I didn't talk about 2+1 because this is work in progress, but you can also write down similarly phases for 2+1.
Yeah, but you could
okay, I think we really should continue this and maybe offline in the coffee break. Thanks for your question. Yeah.
Well, maybe I'll make just one brief comment about that, and then I wanted to ask you a question. So I think that there's a basic definitional thing here about whether it's fine to just talk about quantum field theory on Rn, or quantum field theory needs to make sense on any space-time. And I guess at least if you believe in that there's gravity in the real world and field theory should be able to be coupled to gravity, then you do need to know. You haven't really defined the theory and the ability of being able to couple it to gravity until you've said how to define it on a higher dimensional manifold. I also wanted to say that, for example, in the standard model example that Horacio talked about yesterday, many of us, most of us, certainly me, believe that there are magnetic monopoles in the world at high energies. And although those break the non-invertible symmetry, if it exists, you can still use it to study the scattering of the monopoles, even in Rn, just the scattering that includes monopoles.
Yes.
Now for Sakura, do you have any thoughts about continuous symmetries, say along the lines of this SymTFT or whatever?
Yeah, so there are proposals for SymTFTs for continuous symmetries where there are different constructions. If you focus on abelian, there can be sort of flat backgrounds for U1s, or you just gauge the U1 symmetries, you get a non-topological sim theory in the bulk. It's an interesting sort of way to maybe tie it in also to holographic settings where you have continuous symmetries, you know global symmetry will be gauged in the bulk, so there seems to be like reconstructing holography, basically. In the symmetry context, it's interesting because you can have continuous and finite symmetries form, for example, higher groups, and then studying those will require knowing more about these SimTFTs. Yes, Mukund?
Okay, let's see if there's one more question.
Yeah, so I wanted to go back to your examples in string theory and holography.
Yeah.
So most of the discussion you gave us, the examples you gave us, are stuff that I would have said you can understand in terms of Weisser terms on deep brain world volumes, and that's the kind of the examples you gave. Are there features that are not just contained in the Weisser terms? Are there new features that are in deep brain effective actions that one can infer from this line of reasoning?
So there are some kind of, there were these new brains, I think Ethan is in the audience here, they've constructed some new types of brains that actually then would also become topological defects and symmetry, so it also ties in with the story of new type of brains in space, in string theory, where you know there should be a symmetry, for example, and then you construct the associated brain. So that can also go a bit in that direction, for sure. Yes. But I think one of the points that you sort of hinted at is, in all of these settings, at the moment, it's more like we can construct them in these contexts. Can we actually learn something about it? So the nice thing about in these two-dimensional settings is you really learn something, and we'd like to sort of lift this now to higher dimensions. Thanks.
Okay, last question.
So when I have one of these phases that you're mentioning like, over here, do I have also domain walls between these new phases? Like, do you know how this could look like?
No, so I mean, the thing I should really go back to is the full phase diagram. I didn't write down the lattice model for you because I thought this might be too scary, but this is basically a spin model with qubits and qubits with parameters, and then you tune them, and then you gap phases, and then the gap phase will transition through, for example, the wrap. So, for example, this trivial phase will transition here, and you will see there's some choices of parameters will become the Ising model, the chain for the Ising spin chain. And then in here, for example, you would have transitions. So these are gapless phases. There's really phase transitions. They're not domain walls. They're really transitions between these two theories in this phase space of this spin model that you can write down in this case. So.
Okay, very good. So I think we should give another applause to Sakura.
Thanks.